So today we're going to look at the electronics cooling module within SolidWorks. And as most of you guys know, computers are taking over our world. And not only that, they're getting smaller and smaller. And as time goes on, we're demanding a lot more processing capability from our electronics. And that quote there, I say that in kind of jest a little bit, but it's very true. Anybody that's done any thermal engineering before, whether you're a scientist or designer or engineer, knows that as computers get smaller, we're having to take much more aggressive measures and be even more innovative to dissipate heat and keep components in our electronics at safe operating temperatures. So let's look at a few thermal management techniques. We have the classic heat sinks. In this case, actually one thing we're going to look at today is a radial heat sink, and this is a high-performance heat sink here. We have thermoelectric coolers, and thermoelectric coolers have been around for a while, and they're really great at achieving really low temperatures. However, they cost a lot, and when I say they cost a lot in energy. And we also have computational fluid dynamics, and CFD programs have been around for a while. SolidWorks Flow Simulation, for instance. It's a great tool to help us better understand airflow and how heat's moving in complicated systems. So some challenges that we face when it comes to thermal management. Well, we have complicated resistance networks, and we have heat going in a lot of different directions. We have complicated equations, so if any of you guys have ever done a lot of hand calculations, calculating the heat transfer coefficient, you have very complicated equations for determining the Nusselt number and the corresponding convective coefficient. We have the S optimal, that's the equation for the optimal spacing of two parallel plates. Then we have at the bottom there, we have our equations for calculating the thermal conductivity of a composite structure, for instance, a multi-layer PCB. And finally, we have multiple modes of heat transfer. Sometimes we're dealing with radiation, conduction, and convection all at the same time. So what are some of our needs? Well, we need accurate results quickly. We don't want to have to build prototypes. We don't want to have to sit there and hand calculations because time is money. We need to be able to simulate real-world models and scenarios and eliminate assumptions. When you're getting the farther away you get from a real-world scenario, you're having to make a lot more assumptions, and so your results may not be as accurate as you'd like. And finally, we need to be able to test different scenarios without having to build costly prototypes. We don't want to have to, make 5 different prototypes to test 5 different scenarios. That's expensive and time-consuming. So let's take a quick look at what we're going to see today. We're going to explore the built-in database within SolidWorks Flow Simulation, the electronics cooling module. We're going to look at setting up a model. We're going to look at how to apply a rotating region to our heatsink. And finally, we're going to look at thermoelectric coolers and the Peltier effect and how we can simulate that within SolidWorks Flow Simulation. So the database, what's available? Well, we have a very large predefined database of components, fans, different geometries, materials, and much more. We can also customize this and define our own materials and databases. So let's go ahead and jump into SolidWorks here and take a quick look at the material database. So I'm inside of my SolidWorks Flow Simulation, and I'm going to go up here and I'm going to select my engineering database. So this window pops up, and you guys can see here that we have quite a bit to choose from that's built in. We even have cities right here, so if we're doing like a radiation analysis, we can actually position where the sun is in the sky and what time of day and how the radiation from the sun is actually being incident on a particular surface that we're analyzing on the Earth. We can apply contact resistances, thermal contact resistance. Let's take a quick look at our fan database here. So we have a large database of fans that are predefined. For instance, let's take a look at a delta fan and what kind of information is contained in our fan database. We'll just select just anyone at random. So we have the name here. We have the hub diameter, the outer diameter, the speed that the fan's rotating at. We also have the fan curve as well. Now we can make our own fans. So if a fan that we find on the internet or from a supplier isn't in the database, we can actually go in and create our own fan curve and our own custom fan, which is really nice because that gives us a lot more flexibility. We have a large database of materials from liquids to solids to steams, and once again we can customize this to our liking. So for instance, solids, we have a lot of predefined solids, metal alloys, semiconductors, and like I said, we can do user-defined materials here. The next thing that's really nice is perforated plates. Now, perforated plate, if you have a mesh on, say, an intake of a box, but it has a lot of holes in it, well, that could be very complicated to simulate in flow simulation because your mesh density has to get really high at that point. So a perforated plate basically takes into account that geometry and defines the pressure drop there. Same thing with porous media. If you want to look at like a filter, for instance, air flowing through a filter, and you want to see what the drop is in your system based on that porous media. One other thing that we're going to look at today is a printed circuit board. Now, there are some predefined printed circuit boards here in our system, but more often than not, you're going to be defining the PCBs yourself. For instance, let's take a look at the one that I created for the study we're going to see today. Let's see here. So this is a 6-layer board. So to define a printed circuit board, we need to define what the characteristics are of the conductor material. In this case, it's copper. And for our insulator, in this case, it's FR4. We're going to go in and actually we'll put in the material thickness. And then what we'll do is we'll go in on each conducting layer. We're going to tell it the thickness of the conducting layer, whether it's 1/2 ounce, 1 ounce, 2 ounce copper, etc. And then we'll get the percentage fill factor to apply. Then it's actually going to calculate our thermal conductivities for us, which is really nice. Finally, the last thing I want to look at is how we can deal with actual components. Now, what we do in flow simulation, we have a 2-resistor component, and that models the junction in the case as 2 bodies, and we define what the RJC is, the resistance from junction to case, and the RJA, the resistance from junction to the board is. So for instance, we'll look at this Intel CPU. All we do is we give it a name, we come in and tell what the thickness, the length, and the width is, and then we define what our RJC and RJB are. So that's kind of an overview of the engineering database. Next, I want to look at setting up a model. Now, what we're going to do here is we're going to apply a 2-resistor model to a CPU. We're going to use a 6-layer board with FR4 as the insulator. We're going to apply a 75-watt load to that CPU. And then we want to make sure that our junction temperature of 100 degrees C, our max junction temperature, isn't exceeded. And finally, we have an ambient condition of 28 or 38 degrees Celsius, or roughly 100 degrees Fahrenheit. So let's go ahead and jump back into the model here and look at how we can simulate this. Now I'm going to go ahead and activate this other configuration, and let's go ahead and turn off my results plot. Let's take a quick look about how we would define all of this in SOLIDWORKS Flow Simulation. So in this case, we're actually going to apply a fan from our database. So what I've done is I've modeled a lid. It's just solid geometry, and we're going to define an external inlet fan. So I'm going to go in here and edit the definition, and here we go. So I select my fan from my database. I basically just select the face that I'm going to apply that fan to. I give it a inlet air temperature, and I define external inlet fan. And that's all I have to do to define the airflow from this particular fan that we've created. Now, when I want to start a new calculation, what I like to do is I like to actually step through the wizard. So if I was defining this from scratch, I would just give it a project name. And we'll call this CPU fan analysis. We can select what configuration we're using from our actual model and have a couple of different configurations here. We'll just say current. We'll say next. Now here we can define our units. We'll just take the default. In this case, we're doing an external analysis. So I'm going to select external, and we'll exclude cavities without flow conditions and exclude any internal spaces that exist within our model, so anything that's hollow. I want to define heat conduction in solids, and I also want to define gravity because there is some natural convection effects going on in this case. And so we have that set to our y-axis here. We'll go ahead and say next. Then I want to select what gas I'm using. So I'm going to select air for my gas. I'm just going to double click that. Go ahead and say next. And then I want to define my default solids. So in this case, we'll just make our default solids aluminum. We'll say next. Surface roughness we'll ignore. And then our thermodynamic properties. So here, for instance, I said it will be 38 degrees C, 38 C. We can just enter that. And it changes it for us. And we're ready to go. We hit next. Now we can set our default mesh parameters. And so we'll go ahead and set 3 for our resolution. We can adjust this, as we like to make it more fine or slightly more coarse. For an initial analysis, we'll run it around the 3 or 4 region to get our first results. I'm going to go ahead and hit cancel here, and we're going to go back to the model. So let's look at how we can define our 2-component resistor. So let's go ahead, and what's really great about SOLIDWORKS Flow Simulation and all of the simulation products is that you're working inside of the SOLIDWORKS environment. So I can actually access, well, we'll come back to that here. So my 2-component resistor, I'm going to edit definition here, and if we zoom in, we can go ahead and hide the heat sink, the copper core, and let's hide these mechanisms right here. Let's hide the heat sink, hide, and then we'll hide the retention mechanism so you can see this a little better. So we select our case body, and so this is actually an assembly of 2 parts. So we have our case, our junction body, and I have another component here which is just a copper conductor to bridge the gap between the top of the case to the heatsink. So that's pretty much it. We define those 2 components, the junction and the case, and the thermal resistance for the RJC is actually modeled as an infinitely thin plate between these 2 solid bodies. And then our junction to board thermal resistance is actually modeled as an infinitely thin plate, or basically a contact resistance between the board and our junction here. So that takes into a lot of complicated physics into account pretty easily for us. At that point, we can go ahead and define our heat source, so our load of 75 watts in this case. And when we run our analysis, what we're going to be looking for is the actual temperature of our junction body in this case. And it should be pretty isothermal. And it looks like I accidentally changed. There we go. We'll just X off this. Finally, let's look at applying our printed circuit board. So I would actually go into Flow Simulation here, and this is actually where you would start defining, like I said, your 2-component resistor, contact resistance, a heat sink, or any other conditions. So I select define printed circuit board. I get this option showing up in my feature manager design tree. we just select our board, we go through our database, find, in this case, it was my 6-layer board that I defined earlier, and just apply that. So let's go ahead and turn back on our other bodies. So we've got our fan, copper core heatsink, and retention clip. We'll go ahead and show these again. There we go. So at that point, we're ready to mesh the model and run it. So let's take a quick look at our fan, at our results in this case. You'll notice that we defined a couple of goals. So I've got a couple of global goals for max velocity and average velocity. We defined average temperature of the solid, and that's actually of the junction, and a minimum temperature of the solid here. So I've got my results loaded. Let's go into cut plot 1. So a cut plot is basically going to cut the model, and it's actually going to show us what the temperature or whatever parameters that we want to look at in this case. So we're just going to use the front plane as our cut plot. We could select another plane from our model tree here. We could do right. We can define an offset in that case. We're going to do a contour display, and we're also going to show the vectors, and that way we can see what direction our air is actually flowing. We can change our contour resolution as well if you like to, and show this. So this is a simplified model of a fan with a 75-watt heat load on our chip, and here we're able to look at the temperature distribution through our model in that cut plane. We can see that our maximum temperature actually does occur at our junction like we would expect of 59.9 degrees C. So we're looking at about a 32 degree temperature rise from junction to ambient. We're below our max junction temperature of 100 degrees C, so we're good to go in this case. You can also see the vector profile here, or the vector plot of the actual airflow in the system, which is really nice, so we can better understand how air is moving through this system due to our fan. So next, I want to look at setting up a rotating region. And a rotating region could be necessary for a couple of reasons. Maybe you're designing an impeller. You want to look at a pump design, for instance, and how the impeller of the pump is actually moving the fluid. You may also want to look at the fan blade, for instance, like we're going to do today. There are scenarios where a rotating region with a fan is necessary. For instance, if you have a scenario where a fan is up really close to a wall, that system resistance due to that increase in pressure of that fan being really close to the wall is actually going to change the fan dynamics. So your original fan curve isn't the best, isn't necessarily applicable at that point anymore. And we've actually seen this with some customers and seen this in practice before. So it's one reason I wanted to model a rotating region in this case, because the fan is sitting right on top of this heat sink, and I wanted to ensure that my simplified model of just selecting a fan from the database was accurate. We're going to define a fan speed of 4,400 RPM in this case. So let's go back to SolidWorks. Let's activate our rotating region. And I'm going to go ahead and turn off the results here so we're not jumping ahead too far. So to define a rotating region, we have to do a couple of things. First of all, we need to actually model the geometry for the rotating regions. So let's take a quick look at what we have to do that. So here's my rotating region part. I'm just going to go ahead and open this. And the rotating region is all of the air volume that the fan blade actually moves in. This is actually a solid body in this case. And the one thing that's important here to note is that to define a rotating region, it has to be defined as a revolved profile. So we basically just create a sketch, revolve it 360 degrees, and we've got a rotating region created. We'll go ahead and close this, and we'll go back to the model. At this point, we would go ahead and just assemble the rotating region over our fan. So that does create an interference there between the fan and the rotating region, but because we're going to define this translucent solid body right here as a rotating region, we won't have any issues with interference interferences in that case. So we're actually going to look at how this fan blade, the actual physical dynamics of that, affect our fluid flow. So to define a rotating region, we would just go under Flow Simulation, select Rotating Region. We'll actually do this. I select that region. You'll notice here we have a couple of arrows, and we have an arrow pointing down, which shows us the direction of our airflow by default, and we also show what direction the fan is going to spin, fan blade is going to spin. So in this case, I want to make it minus, we'll say 460 radians per second. Actually, let's make this positive 460. There we go. That way we have the correct direction for our airflow. 460 radians per second, same as 4,400 RPM. So defining a rotating region is actually pretty simple. It may sound scary at first, but it's a pretty simple process. We'll keep everything the same from the other simulation, and at this point we'd be ready to remesh and run the analysis. So let's go ahead, and this time I want to first look at a surface plot. So to create a surface plot, basically just selected the heatsink solid body. And so that's really nice because we have a lot of surfaces there, and we don't want to go through and select each one. We're going to look at the actual temperature distribution in our heatsink at this point. We'll let this load for a second. It's got a lot of surfaces to generate. And of course, SOLIDWORKS is going to close on me. So just bear with me a second. Once it shuts down, I'll open this back up and we'll keep rolling. Go ahead and restart SOLIDWORKS. Now, it looks like we got a question here, so let me show the control panel and see what we got while we're waiting for this to come back up. So the question is, do you have validated CFD examples with published experimental results? Accurate are they? We actually do, and I can direct you guys to that later. We'll send out an email with some of that information, but we have a lot of validation studies from external flow to internal flow with fans, even the perforated plates, where we're actually doing real-world scenarios, and we also have a lot of theoretical studies too. So where we've actually gone through and done hand calculations to for a more simplified model and come back and model the same geometry with the same conditions that you might do in like an academic scenario in SOLIDWORKS, in Flow Simulation, and match the results. So the answer is yes, we do have validation models that we can provide you with. Okay, looks like it's back up. Let me go ahead and reopen this. No, hold on a second. Any more questions while we're waiting? Okay, let's go back and I'm going to show, forgive me, I've got the, there we go. So let's show the heatsink. And let's go back in and I'm going to activate my rotating region. There we go. Let's load these results. Well, looks like I might have lost a little bit when it crashed on me. Let's see if we can load this. There we go. All right, we won't select that surface plot at this point. I'm going to go ahead and just show the cut plot cutting through the front plane. So here, let's go ahead and actually I'm going to redefine this. So it looks like it's pulling the wrong information. So we'll change this to temperature, set it to 20, and we'll hit accept. There we go. So we've got our temperature distribution in this case. It's pretty similar to what we had before. There's a little bit of difference that you'll notice here. Actually, our maximum temperature is actually 76 degrees C in this case. So what that kind of tells us here is that modeling this geometry with a simplified fan probably isn't as accurate as modeling it with the rotating region, because there's a little bit of system resistance due to the radial heat sink that the fan is sitting right on top of. If the fan was far away from that heat sink, then modeling the rotating region and modeling the actual fan itself, from the fan database as a simplified model, you'd expect to get very similar results. These are close, but they're a little bit different. So we know that our analysis with the actual fan itself in the model is more accurate. So the last thing I want to look at is another application using a thermoelectric cooler. So how low can you go? Well, with enough power and the right TEC, you can achieve really low temperatures of a component. We'll also look at another application outside of the model we were just looking at cooling a canned beverage. Everybody likes to have cold drinks, and the Peltier effect. So thermoelectric coolers operate on the Peltier effect. If that's something that you're not familiar with, it's basically the direct conversion of temperature differences to electric voltage and vice versa across a semiconducting material. So I'm going to go ahead and activate my TEC. So actually the one I was just looking at was the original model. Forgive me for this, I actually got those two confused when we were looking at the results here. So actually the TEC is what I just pulled up a minute ago. So to define the TEC, let's go ahead and actually what I'm going to do here is we're going to utilize an exploded view. And this is actually one thing that's really nice within SOLIDWORKS Flow Simulation, is that we can explode our assemblies. I'm going to hide this cut plot. And that way we have access to the components in our model. Let's go ahead and show this. And there we go. So to define the TEC, I'd go back under Flow Simulation, select thermoelectric cooler, and create a new TEC. So let's look at some of the information that's necessary to define our TEC. So we do have quite a vast database of predefined thermoelectric coolers. Basically what we do is we go in and we select the solid body that represents our TEC. And then we select the face, that's the hot face. And the hot face is actually going to be the top side of our TEC, and the cold face would be the face that's actually connected to the component that we're analyzing here. So let's go ahead and open up this PT8 TEC. We'll look at some of the properties here. So to define the TEC, we need to define some parameters here. We need to define the maximum heat pumped at particular temperatures. In this case, since we're trying to dissipate 75 watts, we're actually going to select this PT8 because it works, it covers that range of 75 watts from 73 to 82. Some other information that's pertinent is the maximum voltage. So this thermoelectric cooler is operating around 14 to 16 volts. Our current strength is about 8.5, and then our maximum temperature drop. So we can achieve almost a 70-degree temperature drop with this TEC. But it does come at a pretty high cost because we're running at almost 8.5 amps and almost 15 volts, which equates to about 127 watts. So I'm going to go ahead and collapse my exploded view. And that's basically the only thing that I did different between the last model and this model is I added the thermoelectric cooler. And we'll see how low we actually can get our junction temperature. So let's show our cut plot. And God forgive me for getting these mixed up a minute ago. Our junction temperature in this case has been brought all the way down to roughly 1 degree Celsius. So that kind of shows you the power of the TEC and this heat sink together. We can actually achieve very low junction temperatures. Now, why would that matter? Well, if we were operating in an extremely hot environment, we want to keep our delta T as low as possible. Semiconductors at very low temperatures are actually more efficient. And so I actually had a problem in the past where we did a similar analysis. One thing that we actually had to deal with was actually condensation on the PCB because we got so cold that we approached the dew point of the air, and so we had to actually deal with humidity and air temperature at that point and figure out how to prevent condensation. So it's a pretty powerful way to dissipate heat is the combination of a heat sink and a thermoelectric cooler. So let's go ahead and kind of review what we looked at today. We looked at the database and we looked at how we can make, how we have a lot of real-world information right at your fingertips. We set up and run a simulation in a very familiar environment. SOLIDWORKS Flow Simulation, just like all the other sim products, work right inside SOLIDWORKS. We looked at setting up a rotating region, which was pretty simple. We can model fans, pumps, any kind of impeller. And finally, with thermoelectric coolers, you can really take your thermal management to the next level. And we've made complicated physics and equations pretty simple, utilizing some built-in capabilities here. So that said, that kind of sums up the presentation for today. I want to thank you guys for joining, and we'll take a few minutes for any more questions you may have.
Everyone can go ahead and type their questions into the questions box. Sam, I think we have a couple more questions there. The first one is, what's the time duration to obtain solutions through simulations?
It depends on your mesh density, and it depends on your processing power, and possibly, you know, how cool you're keeping your own computer. Just kidding, but that's actually very true. These simulations that I ran with the rotating region took about 10 minutes to run. The lower the mesh density, quicker they're going to run. I've run some simulations in, you know, less than a minute. They're simpler, but the more complicated your system and the higher your mesh density, yeah, it's going to take a little bit longer to run. It could take, like I said, anywhere from, you know, a few minutes to just depends on, you know, how refined your mesh is. Let's see. Could you share some info about relationships between mesh points and mesh time? Yeah, I mean, that's kind of what we were just talking about there. Certainly, the more dense your mesh, the longer your solution time is going to be. So you want to have, you know, pretty good system as far as your CPU. Quad core is generally pretty standard. Let's see. So another question, what's the mathematical method behind the code? Is it volume or FEA? Well, it's the CFD program is based on the finite volume method. It actually does work in conjunction. We actually can export our CFD results into a simulation, for instance, if we were wanting to calculate pressures based on airflow back into SolidWorks simulation and actually run an FEA analysis based on the results we obtained in flow simulation. So SolidWorks Flow Simulation is the finite volume method. It uses finite volume cells, but we actually can export some of that data into SolidWorks simulation and use that to run an actual FEA analysis. Let's see. It's asking, are you going to do any examples of PCB heating? I don't have anything ready to show at this time. I can certainly talk with you in a little more detail about that on the side if you like. Heather can shoot you my contact information, Richard, and we can look at that in a little more detail if you like. As far as conduction through the printed circuit board, I suppose that's what you're really referring to. Now, the model that we did look at today, we were actually looking at conduction through the PCB, so we were looking at natural convection and conduction through the solids. So that's why we defined that PCB as the six-layer board, so we could look at actual some amount of heat dissipation from the components into the board.
Okay, are there any other questions? Sam, did we get them all? It looks like we did.
I think so.
Okay. Not seeing any other questions, we'll go ahead and close our webinar for today. I thank everyone for joining us. If you do think of a question after the webinar, please email info@moderntech.com, and we'll be in contact with you with answers to your questions. As I said, we will be sending this webinar out via email, so you can view the recording again if there's some parts that you missed or someone you would like to share this webinar with. Again, thank you so much for attending today, and thank you, Sam, for a great presentation, and we hope to see you next time.
Thank you, Heather. Thank you guys for joining.